Hey everyone, if you are a sixth semester VTU student staring down your embedded systems design exam, you are exactly where you need to be. Welcome to The Explainer. Today, we're unpacking the absolute essentials straight from your model question paper, and we're going to build a solid mental map of how all these core concepts actually connect.
I want you to think about this question for a second. How exactly do raw physical hardware gates and lines of digital code merge to perfectly execute just a single, dedicated function? Well, that question is the very heart of embedded systems. Over the next few minutes, we're taking a top-down journey. We'll start at the physical hardware, move up through the operating system, and go all the way to the code abstractions that tie the whole shebang together.
So here is our syllabus and study roadmap for today. We'll be hitting 6 key areas. 1. Defining the embedded system. 2. System quality attributes. 3. Firmware development and languages. 4. Kernels and process logic. 5. The ARM Cortex-M3 architecture. And finally, 6. CMSI and assembly basics.
Okay, let's dive right into this. Section 1. Defining the embedded system. Building the foundation. The foundational defining trait of an embedded system is incredibly specific. It's a combination of hardware, software, and mechanical components designed to perform one specific task only. Unlike a multi-purpose desktop PC that does a million things, this hyper-specialization is the absolute golden rule that examiners are always looking for.
And you know, these systems have evolved dramatically over time. As a high-yield exam checklist, remember the 4 generations. First-gen systems were basic 8-bit microprocessors, like early digital telephone keypads. The second generation bumped things up to 16-bit, which gave us industrial SCADA control systems. Third generation, that brought high-performance 16 or 32-bit digital signal processors and ASICs, perfect for complex robotics. And finally, our current 4th generation uses highly complex system-on-chips and multi-core processors. Basically, think of the incredibly powerful smartphone sitting in your pocket right now.
Now, this setup brilliantly illustrates how embedded hardware physically protects itself. It's an optocoupler, specifically the IC-MC2M, and it safely isolates the input interface from the microcontroller. But here's the cool part. It does this using light instead of electricity. An LED converts the electrical signal into light, and a phototransistor receives it on the other side. So because there's no direct electrical connection, it totally isolates high-voltage parts of a circuit from your delicate, expensive microcontrollers.
Moving right along to Section 2, System Quality Attributes, Operational versus Non-Operational.
This is a classic high-value compare and contrast exam target. Quality attributes fall squarely into 2 different camps. First, we have operational attributes. These matter when the system is live or running online. We're talking response time, throughput, and reliability. Basically, how well does the device do its job in the real world? Then, on the flip side, we have non-operational attributes. These don't rely on the device actively running. Instead, they're absolutely crucial for the engineers who design, test, and upgrade the product. Things like testability, portability to new processors, and evolvability for future tech.
Section 3. Firmware development and languages. The logic that drives the hardware. I'd highly recommend taking a mental screenshot of this comparison because understanding the difference between standard C and embedded C is vital here. Standard C is mostly for desktop apps and usually goes through OS APIs. But embedded C, it's purpose-built for microcontrollers with strict resource limits. It allows you to directly access the hardware registers and I/O ports. Now the trade-off is that because it's tied so intimately to specific hardware, embedded C is inherently less portable than standard C. And because we're writing code for that specialized hardware, the way we compile it has to change too. A standard compiler converts source code into machine code meant to run on the exact same system it was compiled on. Like you write a Windows app on a Windows PC, right? But for embedded systems, we use a cross-compiler. Here, you write and compile your code on a powerful PC host, but the compiler generates a binary specifically tailored to run on a completely different target system, like a low-power microcontroller out in the field. But hey, sometimes even embedded C isn't close enough to the metal. That is where assembly language steps in. The upside? You get the absolute maximum performance, incredible memory optimization, and direct low-level hardware access. You are fully in control. The downside, of course, is the sheer difficulty. Writing assembly is slow, it spikes your development time, and you need a really intimate understanding of the target processor's architecture. Let's step it up a layer to Section 4. Kernels and process logic, managing the system's brain.
If your embedded system is complex enough to need an OS, the kernel is its core. And it's fascinating to contrast the two main designs here. A monolithic kernel is an all-in-one approach. All OS services, memory management, file systems, everything run together in kernel space. It's super efficient, but it's bulky, and if one tiny service crashes, the whole system goes down. A microkernel is totally different. It keeps only the absolute bare essential services in the kernel space, moving most operations out to user space. It's a highly modular and much more fault-tolerant design.
Within that OS, we really need to clarify the execution hierarchy, as it's a common area of confusion. We start at the bottom with a program. That's just static code sitting passively on a disk, doing nothing. When the OS loads that program into memory to actually run it, it becomes a process, or a task, and it gets its own dedicated memory space. Finally, we have a thread. A thread is just a lightweight process that shares the memory and resources of its parent process, which is what allows for really efficient concurrent execution.
Now, what's really interesting is how we model behavior when we don't have a full OS. We often use a finite state machine, or FSM. If we trace the path for a coin-operated telephone, we start at state A, the ready state. The specific event of lifting the receiver transitions the system to state B, where it waits for a coin. The coin insert event moves us to state C, waiting for a number, which eventually leads to dialing. FSMs visually map out every possible valid interaction loop your embedded logic needs to handle.
Let's shift our focus to the hardware brain. Section 5. ARM Cortex-M3 architecture. Deep dive into the processor.
For the later modules of your exam, this is the specific hardware you need to know. The Cortex-M3 manages security through 7 distinct processor modes. Notice the key difference here. 6 of these are privileged modes, like supervisor, system, and various interrupt modes. These privileged modes give you full read-write access to the main control register, the CPSR. But there is only one non-privileged mode, which is the user mode. In user mode, your software is highly restricted and only has read access to the control field.
When we break down that program status register, or PSR, 2 major fields jump out. The control field contains the current processor mode we just talked about, along with the interrupt mask bits. Meanwhile, the flags field holds your condition flags: negative, 0, carry, and overflow. If you're executing branch instructions in assembly coding, these flags are absolutely vital.
And that brings us to our final stop, Section 6, CMSIS and Assembly Basics, standardizing the software interface.
Imagine writing low-level code for dozens of different microcontrollers. It would be a messy, massive headache, right? Enter CMSIS, the Cortex Microcontroller Software Interface Standard. It acts as the ultimate universal translator. Instead of your application code having to talk directly to raw silicon, it communicates with the CMSI core. This core layer provides standard names for registers and peripherals, neatly bridging the gap all the way down to a specific vendor's silicon.
So the crucial takeaway here is that CMISS saves developers massive amounts of time. By providing hardware abstraction through common interfaces, it guarantees code portability. That means you can write code for one Cortex-M processor and reuse it on a completely different vendor's chip without having to reinvent the wheel. Plus, it standardizes toolchain integration, so your debugging and tracing tools work consistently, no matter what board you're hacking away on. All right, let's wrap this up by quickly proving you can trace a simple assembly logic loop. This snippet adds the first 10 integers. First, we load the number 10 into register R1 to act as our counter. We clear R0 to 0, that's going to hold our sum. Then the loop kicks off. We add R1 to R0. Next, subs subtracts 1 from our counter R1 and crucially updates the status flags. Finally, BNE loop checks the 0 flag. If the counter isn't 0, it branches right back up. It just repeats that cycle until R1 hits 0, leaving our final calculated sum perfectly resting in R0. And there you have it. You've just built a complete mental map of the system, from bare metal hardware gates all the way up to SysVis abstractions. With this architecture fully understood, the only question left is, what complex system are you going to build next? Best of luck on that VTU exam, stay focused, and keep exploring.